Hello everyone, welcome again to this online course on fundamentals of composites and cellular materials. For the last few classes, we are talking about advanced composites. Basically, I have come to the almost to the end of this course where we are discussing about advanced composites, and in these advanced composites, I have talked about advanced metal matrix composites. I have talked about advanced polymer matrix ceramic matrix composites, and now the plan is to talk about certain processing techniques, advanced processing techniques, which are used to make advanced composite. So, in this class, my plan is to discuss on spark plasma sintering. I have mentioned certain examples, I have given certain examples where SPS or spark plasma sintering has been used as a sintering technique, and I have not provided details of SPS earlier. So, I think I should give you some details on SPS, and that is the reason this class I am taking. So, advanced composites we have classified into 4 sections: advanced MMCs, advanced CMCs, advanced processing techniques for advanced composites, and finally, application oriented advanced composites. So, I am talking about advanced processing techniques in this class, and the one which I want to discuss is SPS. So, you can see here a very simple schematic of the SPS machine. Okay. So, what you have here, there is a you can see here a graphite die. In this graphite die, the powder particles or the mixture of powder particles are loaded. So, in this sintering, contrary to conventional sintering, in this sintering we do not need any green compact. Okay. The powder is directly loaded in the die, and then there is a uniaxial press, as you can see here, which applies a very high amount of load, and during application of load also there is a DC pulse generator, which actually applies a DC bias voltage, pulsed DC bias voltage in this to these punches, to these punch sets in the die. Okay. And obviously, you have different kind of temperature measurement you need, you have different kind of pressure measurement you need and all those things, but in nutshell, the powder is loaded in a die and then simultaneous application of pressure and DC pulse power, okay, and that leads to very good densification. So, the plan here is to understand why this kind of densification we achieve in SPS. So, as you can see here, it says simultaneous application of pulsed DC current and pressure enables rapid consolidation to form dense CMCs. All right. So, let us see how it happens. It says that generation of plasma leads to incipient fusion and fast sintering. Okay. This is what we need to understand. It says that generation of plasma leads to incipient fusion and fast sintering. So, in our today's class, we would like to understand this portion. Okay. And what are the advantages of this process? So, it says it leads to only surface heating. So, if you have powder particles which are being sintered, only the surface of the powder particles get heated. Internally, or the internal structure of the powder particles does not get heated that much. It does not mean that it will not be heated at all, it will be heated, but temperature will not rise to that high temperature. Okay. Lower sintering temperatures, as I mentioned earlier, the requirement of sintering temperature is lower here, high heating rate and short sintering time. Because of low temperature and low time, less time, the initial, and also you can see here the surface only gets heated. So, the initial microstructure of the powder almost gets retained, it does not get disturbed. For example, grain growth gets restricted. Okay. If you have some metastable phases initially, those metastable phases gets retained more or less, and finally, there will be excellent densification. So, how this thing happens? Let us move on and let us see. So, what it says here that SPS is based on electrical spark discharge phenomenon. A high energy low voltage spark pulse current momentarily generates spark plasma. Okay. So, spark discharge leads to spark plasma, and that leads to, and I will draw these things so that you understand it better, and that leads to high localized temperature. Okay. And ultimately because of that there will be optimum thermal diffusion and there will be very efficient sintering. As you can see here, the temperature is generally 200 to 500 degrees Celsius lower than conventional sintering. Okay. So, we do not need to heat at a very high temperature, it gets sintered at lower temperature and shorter time. Okay. You can see here, conventional sintering takes around 1 to 2 hours depending upon your material. However, here you can actually finish in 5 to 20 minutes only. So, the time requirement, the sintering time is also quite less. Okay. Now, why this thing happens, how this thing happens? Let me briefly show you that what exactly happens in this case. So, let us say these are the two powder particles. Now, as bias voltage is applied, we can consider one as positive and other one is as negative. Okay. Now, what do you have? What do you have in this area, in this empty space? What do you have? These powder particles, after getting loaded, it gets filled with certain amount of argon atmosphere. Okay. So, certain amount of argon partial pressure is created here. So, there will be air atoms in here in this space, right. And once this bias voltage is applied, as you can see, we can consider one as positive or another one as negative, and because of this bias voltage there will be spark generation, and this spark will, what will be doing? It will, or this arc, what it will do? It will actually ionize the argon gas. So, this becomes now air plus, and ionized gas, what do we call that? We call that plasma. Now, this plasma would be having extremely high temperature. What kind of temperature I am talking about? In the range of 10,000 to 15,000 Kelvin. That kind of high temperature it will create. But whatever is happening only on the surface of the powder particles. So, because of that high temperature, two things will be taking place. Okay. First thing is that this argon, because of its now positive ions, there are positive ions. So, what they will do? They will heat at a very high velocity on these surfaces. At the same time, because of creation of very high temperature, what will be happening is that there will be incipient fusion, or only few atomic layers will be getting fused at that high temperature. Because of very high temperature, there will be a few atomic layer will get molten at a very high rate, very fast, and this molten, because of high temperature, those will get vaporized, and these vapors will create clusters. So, let us say these green balls are the vapor clusters. Okay. And these vapor clusters, on which direction they will move? They will be having Brownian motion. So, they will be hitting anywhere, any side. Okay. Okay. Now, because of these argon ion movements, which is basically having at a very high, basically bombarding at a very high velocity on this surface, at the same time these vapor clusters, they are also moving randomly and hitting on the different surfaces of the powder particles. Because of that, there will be surface cleaning. Okay. So, this particular process is called SIP, spark impact pressure, and because of spark impact pressure, what will be happening? Surface cleaning takes place, surface gets cleaned. Okay. So, surface becomes free of any contamination, surfaces becomes free of any oxides, which could lead to restriction of the sintering, or which could lead to restriction to the diffusion during sintering. Okay. And at the same time also there is, as I mentioned earlier, there is this layer is also molten little bit, and also what is happening, there is application of high amount of pressure at the same time. Okay. So, now you have nicely cleaned surface and you have a very thin layer of molten layer, okay, and application and pressure is being applied. Because of that, there will be very efficient neck formation. Formation, which is the first stage of any sintering process. Okay. So, all these things would be taking place in very less time, okay. And because of this neck formation, because of this loading and everything, so there will be instantaneous sintering of the powder particles at very less time. So, now the whole powder particles gets, so in this process all the powder particles now gets sintered together in very less time. And what is happening here, whatever is happening, this is also very interesting, this is the most important thing I would say, is that whatever is happening in this layer, okay. But internal structure of the powder particles, here nothing really is happening that much, the temperature does not really rise that much. Okay. So, because of all this phenomenon, there will be very efficient sintering, there will be extremely good densification at lower sintering temperature and lower sintering time. Okay. That is why SPS is so important. Now, the process has been mentioned here as well, it leads to creation of spark plasma, and then I have mentioned about spark impact pressure, that phenomenon takes place. There will be certain amount of Joule heating also. Once there is neck formation like this, then there will be Joule heating only, okay. And as I mentioned that there will be enhanced diffusion because of this surface cleaning and because of creation of a very thin molten layer. At the same time, simultaneously there is uniaxial pressure application of high amount. All this would lead to extremely good diffusion, extremely good sintering. That is the basic sintering mechanism in spark plasma sintering. Here I need to give you one more information, is that there are people, there is a group of researcher who do not call it is as SPS, because they do not believe in the idea of spark generation and this plasma generation ultimately. So, they call it as FAST, which means field assisted sintering technique. So, SPS process and FAST process are basically similar, the names are only different. In some cases, in most cases people use SPS, in some cases you will also be seeing people are calling this process as FAST or field assisted sintering technique. All right. Now, let us understand, let us now, as we understand this SPS process, now let us see using SPS process, let us try to make an advanced composite material. Okay. So, let us move on, let us go to a new example. So, the example which I want to give now is graphene nanoplatelets reinforced aluminum nanocomposite. Okay. So, in this case graphene nanoplatelets have been used, these are high strength material, these are nanoparticles. Okay. So, hard nanoparticles would lead to extremely good composite strengthening. First of all, extremely hard. So, that will obviously give you better strengthening effect, composite strengthening effect. Secondly, because of smaller size, because of nanoparticles, nano size, the number density of those particles will be very high. Even if you have a less amount of this material is used or less volume fraction of this material is used, the number density will be very high. Because of higher number density, the mean free path between the particles will be less. When the mean free path between the particles is less, that gives better composite strengthening. The load transfer efficiency improves. I have mentioned it few times, okay, that when the mean free path between the reinforcement particle decreases, the load transfer mechanism becomes more efficient. And if the particles size in the nanometer range, it could actually interact with dislocations also and could lead to dispersion strengthening as well. So, composite strengthening, dispersion strengthening and very efficient load transfer during composite strengthening. That is why these hard nanoparticles are used. You can increase the strength also by making the matrix nanocrystalline. Okay. So, that is what has been actually tried here, nanostructure composite with light weight and high strength. So, the matrix as I mentioned here, these aluminum powders, microcrystalline aluminum powders, they have been ball milled to make it nanocrystalline. As you can see here, after ball milling for certain time, using certain parameters, it becomes the powders become nanocrystalline. Okay. And then the reinforcements are basically graphene nanoparticles. So, graphene nanoparticles are basically these graphene sheets, as you can see here. Okay. You can use this graphene sheet to make different kind of allotropes like carbon nanotubes, like buckyballs of fullerene. Similarly, graphene nanoplatelets, basically few layers of graphene where the layer thickness is in the nanometer range. In xy direction, the dimension will be in the micrometer range, but in thickness direction there will be only few layers of graphene sheets. So, ultimately the thickness would be in the nanometer range, and you can see it will be having a flaky morphology like this. At high magnification TEM image, it looks like this, all these flakes. Okay. You also can see the individual layers of graphenes, the distance between those graphene layers is basically 0.34 nanometer, that is standard. Okay. So, now how this has been made, a schematic has been shown here. So, this GNP, because of nanoparticles, okay, the first thing we have to homogenize them properly. So, to homogenize, functionalization is done, physical and chemical functionalization both can be done. In this case, in this example, both physical. So, first it has been chemically functionalized by nitric acid, as you can see here, and then it has been again it has been mixed nicely, and then by SDS. SDS is basically sodium dodecyl sulfate. It is a physical surfactant which actually improves the dispersion of the graphene nanoplatelets in nanoparticles. So, if the SDS gets attached with the on the surface of the nanoparticles, then there will be kind of repulsion between the particles, and that would lead to better homogeneous distribution. So, ultimately both physical and chemical functionalization was carried out to improve the homogenization, and then it has been mixed with aluminum particles. How? So, now you can see this microcrystalline aluminum powder, those have been ball milled to get nanocrystalline powder, and those have been mixed in a certain process. This nanocrystalline aluminum powder and functionalized GNPs have been mixed in a particular manner which has been shown here, and then ultimately it has been, the mixture has been dried and all those things, and then it has been spark plasma sintered. Okay. So, now look into this, let us you can go through this slide which gives details of how the functionalization was carried out. Okay. So, both physical and chemical functionalization was carried out. Just to check if the physical functionalization is done properly, so XPS was carried out, and which shows this ultimately Na1S peak, actually sodium 1S peak, which talks about addition, or basically this SDS molecules gets attached on the surface of GNP. That is kind of a signature of that. All right, Let us look into the morphology. So, these nanoparticles, aluminum nanocrystalline particles with GNP. So, if you see here, and the percentage is 0.58% GNP only. Okay. Now, if you see here that the densification is extremely good. Okay. You do not really see any evident porosity or pores. Okay. So, the sintering process is quite efficient, as you can see here. 0.5% GNP does not lead to any kind of agglomeration. That is why you do not see any porosity. You also can see here that the carbon atoms are well distributed from this particular X-ray mapping. It shows that both aluminum and carbon atoms are well distributed. That again gives an indication that there is good distribution of GNPs, and the matrix after the consolidation, if you see, obviously when it was ball milled, it shows nanograins, but has it been retained? That is a bigger question, that is a bigger challenge, because during sintering there will be inevitable grain growth. So, one of the reason of doing SPS was that SPS leads to good densification, extremely good densification at low temperature, low sintering temperature and low sintering time. So, is that helping in this particular case? Yes. Here also you can see, even after doing sintering, the nanocrystallinity has been retained. Okay. And certain phenomenon you can see here, that around GNP, because of nanoparticles, so they interact with these locations. So, you can see there is pile of these locations around the graphene nanoplatelets. You can see here a nice image, dark field image, which shows a graphene nanoplatelets, and around that you can see this dislocations, how they are actually getting piled up. So, GNP is extremely efficient in in interacting with dislocation and improving the strength in that way by the virtue of giving dispersion strengthening. All right. So, once we understand the microstructure, that it is quite dense, it retains nanocrystallinity, the GNP is well distributed, and the GNP also interact with dislocation. These few points we get from here, and then if we look at even higher magnification by doing TEM, what we see, there is a clean interface between GNP and aluminum. That means, GNP and aluminum at the interface does not react at that less time provided during sintering. Okay. So, basically it has a very clear interface without formation of any kind of interfacial product layer, as you can see here. So, both sides we have, one side we have aluminum, other side we have GNP. Okay. How the grains are also been seen here, an aluminum grain, and at the tip of this aluminum grain there is GNP being residing there, which shows very clear interface. Okay. Let us move on. So, what has been shown here in this particular case, that by XRD, so XRD has been carried out at different stages, okay, and then the crystallite size were measured. Okay. So, you can see as received powder, the crystallite size was in the range of 422 nanometer. Once it is milled, it becomes 38 nanometer. So, ball milling leads to nanograins. Now, this 422 nanometer, if you sinter it as AL compact, okay, without any GNP, then there is certain amount of grain growth. Okay. And if you take, now if you with this aluminum powder, microcrystalline, no ball milling, if you add GNP, you can see here that this 450 is less than 502. That means, GNP is restricting the grain growth during sintering. We are talking about here microcrystalline grain. So, no ball milling, as received powder sintered without GNP 502 nanometer with sintered 450 nanometer crystallite size. That means, GNP is effective in restricting grain growth. Now, let us talk about the ball milled powder. So, I have ball milled nanocrystalline powder 38 nanometer, it gets sintered without GNP, it is 81 nanometer, with GNP 68 nanometer. So, you can see here in this L nano without GNP, there is certain amount of grain growth, and the grain growth is even less when you are adding GNP. So, two things I can ultimately, two conclusions I can draw from here. Number one is that after sintering, the nano grain size has been retained. There is certain amount of grain growth, but ultimately it is still in the nano range. Secondly, GNP is helping to keep the grain size in the nanometer range, okay, or keep the grain size in the lower values. Okay. So, once you understand that, then the main idea of this particular example I am giving to understand the mechanical properties, the effect of all these factors, this GNP addition, agglomeration, grain growth, grain growth restriction, all those things, how it is affecting the the mechanical property. So, tensile testing of this miniature samples were fabricated, basically machined out from the compact structure, and then tensile testing was carried out. So, if you see this black one is for pure aluminum, and here actually we are talking about only micron size aluminum, like there is no this in this case it is not ball milled, this powder. Without ball milling, this was mixed, just to see the effect of GNP now. So, in this particular slide we are just seeing the effect of GNP on the tensile testing results. So, pure aluminum, nice ductility as expected. As there is increase in amount of GNP 0.25, 0.5, you see strength is increasing at a very high rate. So, from it was around 80, the UTS would be around 80, from there the UTS goes to above 160, it becomes almost double, more than double actually, okay, up to 0.5, and it does not lose the ductility that much. You can see it is quite ductile also. However, once there is more amount of GNP, 1 weight percent, as you can see here, okay, that leads to poor strengthening. Why? Because of agglomeration problem. Okay. Till 0.5 thing, the story was good. The moment the GNP content was increased beyond 0.5 or 0.75, you can see there is lot of porosities, and those porosities would lead to premature failure, and that is why you see poor strength in those materials, okay, at higher amount of loading of GNPs. So, you can see the present work where we are seeing here. So, compared to other studies, it shows obviously higher strength, strengthening efficiency is better, okay. And then if you look at the, so this is for micron, that means the grains are micron size. Once the grains become nano size, okay, what is happening here is that now this is the microns 0.58% GNP. So, this one, this blue one now has been taken as the baseline, this black line, okay. This is actually Al micro 0.5 GNP, okay. And then different kinds of powders have been added here, okay. 5 hour milled, 8 hour milled, and then this is 10 hour milled, okay. Higher milling means lower grain size, okay. So, you can see here with higher milling time, with lower grain size, there is increase in the strength. It reaches to around 280. So, you can see we started from 80, we are going to 280 MPa. However, we are losing the ductility completely, okay. So, when you are using nanometric grains, you are actually losing ductility. So, we need to do something to get rid of this problem. In the coming class, in the next class, we will discuss about that how from this problem we have improved the strength, but then how can we also maintain or retain ductility to certain amount with increase in strength, okay. That is what would be discussed in the next class. So, I would like to conclude today's class. I have discussed about the basic sintering mechanism in spark plasma sintering, and then I am discussing about a particular example where the matrix is aluminum, both microcrystalline and nanocrystalline, and this matrix has been reinforced with graphene nanoplatelets, and then we are trying to understand the effect of the microstructure on mechanical properties. So, I will continue on this line. Thank you all.